Okay, so our focus in 6.4 is going to be roses, which when we sketch these, they will actually not look like roses. These are going to look more like daisies. Why they call them roses? They don't look like roses. Okay, so first what we're going to do is take a look in our calculator. You need to clear out your calculator. It is second plus 712. There's a couple different ways, but basically that clears our memory. So when we go into the mode, everything is flush left. Okay, and what we want to do is change our mode from function to polar. So I'm going to go down here, and instead of a function like y equals, this is going to be in terms of polar, which would be r equals. So now when I go into y equals, I see all of these that are r. Okay, so that's going to be for our polar unit. Okay, so we'll start with just two examples so that we can make a generalization, but I just want you to see what happens when we draw these. So what we're going to do first is go into our calculator and put the first function here, which is 5 sine of 2, and see here this is going to be our theta, which normally we would have x, and it just puts in theta, and I graph this. Okay, so this is what a rose looks like. Just like I said, it's going to look like a daisy. And what we want to determine is, without a calculator, how do we determine the number of petals and the length of each petal, meaning what's the longest point. So I'm actually going to zoom square this so it actually comes out more square. And again, that looks more like a 4-leaf clover. But the whole idea here is the number of petals, in this case, is 4. So this way we can determine which of these values that I highlighted we're going to use. And then the length of each petal is going to be based on the rotation, which is more angular. But if you get an idea here, if I were to count, this goes out 1, 2, 3, 4, and the highest point is going to be at 5. Okay, so this is what we have here. Then I'm going to go back into y equals, and I'm going to unhighlight this and type in the next, which is going to be 6 sine of 3 theta. And I will graph that, which is already in a square, and we can see now I have 3 petals. And if you were to count all the way down here, this is actually, the length is 6. So what you can see in terms of a generalization, and we'll do the generalizations in just a second, but the number of petals is based on the coefficient of theta, and the length of each petal is based on the coefficient of the trig function. So let's see what happens. This is when we have sine. Let's see what happens when my trig function is cosine. So I'm going to go in and actually change this one, so now we can see what this looks like, just get a visual. And now I'll go back in here, and I'll just go down here, and instead of sine, I'm going to put in cosine, and let's see what happens. So remember, we had a petal that was on the y-axis. So let's graph this. See how that changed? Okay, so go back into y equals. Let's clear out this function, go up here, turn this back on, and change this to cosine. Look at that. So before, the petals were in each quadrant, and now they're on the axes. So that's something that's actually going to happen. So my recommendation is, at some point, just go back through and take a look at what each one of these looks like, and you can fill the rest of this table in. What we're going to do now is make the generalization. So I've pre-highlighted, so if you want to pause the video, and you can highlight if you're taking notes. You should write all of these rules down if you do not have a note packet. Okay, so these are just standard form of both the polar version of sine and cosine. And you notice here I highlighted the ends in green because up at the top, the coefficient of theta is what determines the number of petals. Okay, so the number of petals is based on the coefficient of theta. So if your n value is an odd number, okay, then you will have n number of petals. So if we go back up here, this was 3, we had 3 petals. Okay, if n is even, then we have 2n number of petals. So here, when we're looking at n, which is the coefficient of theta, this is an even number, so this means I'm going to have 8 petals. This is odd, I will have 5. This is odd, I will have 7. Okay, so I just filled that out for you. Now we have to determine the length of the petal. Okay, and the length of the petal is your coefficient of your trig function, represented by the letter A in the standard form here. Okay, so that's how we determined what the length was, so you can determine the length up here. Okay, so now we have to be able to sketch the entire thing. So the distance, which is really the angular rotation, okay, between the petal points, which is the longest point on the petal, which in this case, if I'm looking at this graph, would be up at the top here, 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 and here. Okay, the distance is calculated by taking 2 pi divided by the number of petals. Okay, so you have to determine the number of petals first. So remember, if n is odd, okay, this will be 2 pi divided by n. If n is even, this will be 2 pi divided by 2n. Okay, you don't want to cancel these out because you want to leave the number of petals in the denominator, because sometimes you will actually need that common denominator. So don't cancel those out. Cosine will always have one petal, okay, that is symmetric to the polar axis. And this is because if I take the cosine of 0, I'm going to get 1, and the cosine of pi is equal to -1. So if I look at my axis here, this is 0, this is pi, okay, you're actually going to plot on the axis itself. Sine never has any petal, never has any petal that is symmetric to the polar axis. Angles, because the sine of 0 is 0, and the sine of pi is also 0. Okay, so just keep that in mind. So sine will have symmetry with respect to theta is equal to pi over 2. Okay, and cosine has symmetry with respect to the polar axis, and this is going to be helpful when we're graphing. And remember too, this is minimal. Okay, it depends on the function that you're given, so you could have more symmetry. Okay, so some additional rules which are on the top of page 14. We're going to take a look at 2 examples. Okay, one is a sine and one is a cosine, and we're already given the actual graph itself. So we want to take a look at how we determine all of these pieces. Okay, so I'm clearly looking at this graph and I can see how many petals I have. I have 3 petals, but when I look, remember you're looking to see what your n value is. So in this case I have 3 petals, and it's because n is equal to an odd number. Okay, when I look here, how many petals do I have? This is going to be 2 times n, which in this case is going to be 8. I highlighted it backwards, sorry. Okay, so the distance between the petals is found by taking 2 pi divided by n. So in this case, this is 2 pi over 3. Okay, 2 pi over 3, because 2 pi is a full rotation. So here, when I take a look at the distance between the petal points, this would be 2 pi divided by 8. Okay, but you might need to leave this as is when you are determining each of the petal points. But if you were asked about the distance, you would say that it's pi over 4. Okay, then here I'm going to look at the length of each petal point. Remember, the length of each petal point is based on your A value. So in this case, I'm looking at my A value. This is 2. Okay, my A value here is 3, so the length is going to be 3. Okay, I ran out of room over here, so now I'm looking at symmetry. The way I determine symmetry is I take a look at, first of all, this is a cosine function, so I'm going to have symmetry with respect to my polar axis here. Okay, but also you can see 1 petal is on here. So if I didn't have this trig function, I was just looking and I see that I have 1 petal on the polar axis, I should know that this is a cosine. You notice here that there is no petal on the polar axis. Okay, that means that I have a sine function. So here this is polar axis. And here we know that this is going to be theta is equal to pi over 2. Okay, so what am I looking at? First of all, I do have a petal point on 0, if the distance between each petal point, I have a petal point here, I have a petal point here, and I have a petal point here, all you're going to do is add the distance. So if this is 0, 0 plus 2 pi over 3, this is an angle of 2 pi over 3. Add again, this is 4 pi over 3. So if you think about your unit circle, this should make sense here. Okay? So when I take a look over here, all right, if I have the distance and it's going to be half, if this is pi over 4, that means this would be pi over 8, and then the distance from here to here is going to be 2 pi over 8 units. Okay, so when I add, this is 3 pi over 8, okay, 5 pi over 8, 7 pi over 8, 9 pi over 8, 11, 13, and 15. And we'll go through on the graph how you get all of these points. But this is just in general and what you would be looking for.